Right. So welcome to class. Yesterday, I introduced the concept of law of conservation of mass, and we specifically applied it to balancing chemical equations. We're in unit 5. And our phenomenon was basically how do we predict and quantify the amount of oxygen that we could produce from the extraction of carbon dioxide? That was the big idea. But that means we got to go back and study what's all the prior knowledge I need to know and skills I need to have to be able to answer that question and do those things. Part of that is one, how to write chemical reactions in the first place, symbols, so forth. It's a lot of convention, to be honest. It's like we just expect you to read right to left. Now, if you're from like ancient Asia, you read left to right. Sorry, left to right. But if you're from ancient Asia, you read right to left. Maybe the convention flips. Right now, we're in America. We're in the Western civilization. We read left to right. So what we've done is we've said reactants on the left, products are on the right. I've talked about a couple symbols, states of matter, things that are kind of important to know, right? And then, of course, I expect you to be able to write compounds via their symbols based on your knowledge of naming rules, right? So that shouldn't be a problem. And then that was kind of review. And then we address, okay, once we get a good equation, we get the right subscripts, the correct ratios of atoms within a molecule. Now we have to say to ourselves, okay, but when we talk about chemical reactions, we're talking about molecules reacting with other molecules. So what's the right ratio between those chemical species? That's where we got into applying the law of conservation of mass by changing the coefficient, the big numbers in front, by making sure whatever I start with, I end with, just kind of rearrange, but the counting is the same, equal on both sides, right? And so that's where we left off yesterday. The first half of class, we're going to spend doing balancing practice. The second half of class, I'm going to get you guys into now types of reactions. You should notice on your workbook that on the balancing reaction sections, you also had a portion that said type. You couldn't have answered that yet. I haven't introduced those types yet. All you could have done was balancing. But today we're going to start looking at the six most common chemical reactions out there. We'll get through about half of them. Okay. But that's the second half of class. But first, let's address balancing. And one of the keys in balancing is being able to spot your polyatomics. So I did a little review. Hopefully you guys are remembering or trying to remember all of the polyatomics you have to memorize and diatomics, right? What's this motto for diatomics? Brinkelhoff. Everyone together. 1, 2, 3. Okay. 1, 2, 3. Okay, you want to know that because it's gonna mess you up. If I say pure bromine and you write Br by itself, all right. So, that being said, you'll warm up. I asked you to name these 4 polyatomics, which, by the way, were chosen by AP students. They thought these were the most important. Okay, NH4 plus PO4 3 minus, CrO4 2 minus, and OH minus. Could someone please tell me the first one? Carlos. Ammonium. Excellent. So I could have ammonium chloride is one example of an ionic compound. Okay. What about this one? The next one. Anyone volunteer? Mika. Phosphate. So I could have phosphate. And here, I'll write the positive in front. I could have phosphate with lithium. And that would give me lithium phosphate. Okay. What about the next one? Jose. Chromate. I could have, let's do magnesium and chromate. For magnesium chromate. Just a couple examples, right? And the last one, which is really important, especially for honors, for your honors lecture video tonight and tomorrow, you just make sure it gets done by tonight and by tomorrow, you know. This is a particularly important one as you start thinking about acid and base chemistry for honors. What is this polyatomic? Aislinn? Hydroxide. Okay, so what if I did strontium with hydroxide? What I would get is strontium hydroxide, and I'd have to have 2 hydroxides. to cancel out and make a good ionic compound. All of this should be review. All of this should feel very comfortable. If it's not feeling comfortable, you need to go in and get more practice. There are so many websites. You could literally just Google ionic compound making practice PDF online and just get a amount of practice. This is truly just repetition. The more you expose yourself to it, the better. There's no other way around it. Okay. Excellent. So I expect you to be quite familiar and able to spot, write the chemical symbols, okay, formulas with the symbols, and name of all of the relevant polyatomics that I had initially put in your notes from unit 3, okay? So then we get to balancing the following reaction. So to balance, one thing's for sure, you gotta keep in mind that the number of each type of atom for it to be balanced has to be equal on the reactant and product side. All you're doing is rearranging. All you're doing is breaking the old bonds and forming new bonds. You're just putting them together in a different way. All of the pieces are still there though. So for this practice problem, I wrote this, what we call actually, this is called a double displacement reaction. Oh, sorry, single displacement reaction, just as a sneak peek. Barium nitrate reacts with pure potassium. This would be aqueous. Reacts with pure potassium, which would totally be a solid, and produces potassium nitrate, which is going to be aqueous, and pure barium solid. And then I asked you to balance it. So, would it benefit you guys if I wrote out the verbiage of how to say it? Or no? Okay, guess not. So, I got nothing from you guys. You're like minuscule head nods. I can't see that. I have the eyes of a grandma. I'm like almost legally blind without my contacts. So like I can barely see. So let's start off with, what do we have in the beginning? Well, I have barium and one of them, according to my unbalanced chemical reaction. According to my set chemical species I have to make. Like these are the species I have to make. These are the subscripts I have to use. This is the combination of atoms to make the compounds I want. Do I mess with the subscripts now that I'm balancing? No, don't touch it. Don't do it, okay? It's like the red button, just don't touch it. It's like when you see like dry paint and it's like paint is drying, don't be the little turd that puts your hand on there. It's like, is it? Okay, don't touch it. Then what I do is I notice that my polyatomic nitrate is kept together from reactant to product. So I just am going to treat it as one unit. So I'm not going to separate anything. So I'm going to say I have two nitrate groups. I don't have 32. I don't have 3 of them. I have 2 of that whole group. And I have 1 K. And these 2 are bonded together. Then I have potassium on the other side, nitrate, 1 of them bonded together, and pure barium. So then what I do is I balance and I say, okay, I don't really have any H's and O's by themselves. So I'm just going to tackle the first one. I'm going to balance out my nitrates. I want 2, but I connected. So I'm going to do 2 times 2. Okay. So that's all great and dandy. So then I look and I see, well, I see a new problem. My potassium isn't balanced. So I'm just going to multiply by 2. And now I'm completely balanced. So I take my coefficients in front I take my multiplying to determine my coefficients in front. And I say, if I don't have a multiple, what is the value then? 1. If I don't actually have anything times anything, I didn't mess with it, it's 1. Do we write 1s, generically speaking? No, not unless I specifically ask you how many are there, then you write the darn number 1. But if I'm just saying, write the darn equation, okay, write the charge. If you put a 1, that's unnecessary. It's like, obviously, if you wrote it, it's there, like it exists, okay? So this would be 1, not gonna write that. 2 for the entire compound, and 1. Done. So, pretty simple, right? We got this. Wait till you hit to the stations. All right, so we're going to take a pause. We have a lot of station problems to look at. If you're at home, just Google some problems. Literally just Google balancing, practice balancing equation problems, okay? And then we're going to resume with the rest of the lecture in a little bit. All right, I should mention that I should probably give you guys an example of how to say this out loud now that we've written out the balance. So what we would say is that our balanced chemical equation reveals this to be that one barium nitrate compound in aqueous solution reacts with 2 potassium in solid state to produce 2 potassium nitrates in aqueous solution and 1 barium solid group. In the solid state. Oh, well, barium solid. That's it. So that's how you might say it out loud. And notice I reveal a ratio between all these chemical species, right? I have 1 barium nitrate for every 2 potassiums. I have 1 barium nitrate for every 2 potassium nitrates. I have 1 to 2 to 2 to 1, right? So we're going to use those in a little bit later. All right, go ahead and try doing some more practice, and then we'll resume with types of reactions intro. For this one, I'm going to address station 1 problem where I have sodium reacts with sodium nitrate to produce sodium oxide and diatomic pure nitrogen. Okay. So what I have here is one thing you immediately notice is kind of weird. It's like, oh, I have 2 sources of sodium. I have pure sodium, and then I have sodium bonded to nitrate, which, by the way, is not preserved. It is not remaining intact from reactant to product. So that means I can't use the trick of treating it like 1 unit. I have to separate everything. So I have 1, 1, and 3. And I end with 2 sodiums bonded to 1 oxygen and 2 nitrogens. Now I start addressing this. I save my oxygens for last because I always save my H's and O's for last. And I say to myself, okay, well, currently I have 2 sodiums total on my reactant side, which is balanced with the 2 sodiums on the product side. My total sodiums are actually balanced currently, but my nitrogens are not. So I'm going to multiply my nitrogen on this side by 2. But that means everything that nitrogen is attached to on the reactant side has to be multiplied by 2. So now it becomes by 2, 2. So it becomes 6 and 2. Okay, which means, by the way, I am currently now at 3 sodiums. All right. So then I got to look at my oxygens. And I say, well, I am currently at 6 on the reactant side, but I need to have 5 more on the product. So I'm going to multiply my, not red, oxygen by 3 on, or 6 on this side. But if I multiply my oxygen on the product side, okay, I'm going to have to multiply my sodium on the product side by 6 as well. Which makes a new problem for me, because now I am at 12 on sodiums on the product side and 3 on the reactant side. So what I can say is, all right, well, currently I have 2 and 1, but I need 10. Well, I have 2 and I could make this sodium and front 10 because it's alone. It's not attached to anything. That's an easy one to adjust to bring up the total. So then what I can do is I can multiply this solo sodium by 10 to get a total of 12. So now I have 12, 12, okay, 2, 2, 2, 2, 6, 6. And you know what? Why did that look so much? Oh, I over multiplied. So here, let me show you what you can do. So right now I currently have 10 sodiums, 2 sodium nitrates, 6 sodium oxides, and 1. Oh no, I'm good. And 1 diatomic nitrogen. And that is my balanced chemical equation for this. So it's just a lot of number tracking. That's why I don't encourage you to do it in your head unless you have a brain that is suddenly gifted at tracking numbers. But it's really sets you up prone for making a lot of mistakes. All right, this next one. How do we feel about that, by the way? Like once you see it, you're like, oh, that's just annoying, but it's totally feasible. It's annoying, but it's totally feasible. So how about this next one? Okay, what we have here is we have aluminum hydroxide reacts with bicarbonate or hydrogen carbonate, but that's kind of weird. We say bicarbonate, and creating sodium carbonate with water. Now, it might be a little useful to actually write water like this, just as a reminder, because what you see is that it's an H with an OH hydroxide. Kind of can be helpful to separate into ions, just visually speaking. So what I say to myself is I start off with 1 aluminum, and I start off with 3 hydroxide groups bonded together. I also start with 2 hydrogens and 1 carbonate group. Sorry, yeah, 1 carbonate group bonded together, because here's why. My carbonate stays intact as well as my hydroxide stays intact if you write water like HOH. So that's why I can use now the trick. I'm not separating the polyatomic. So now I say, okay, I end with, according to my unbalanced chemical reaction, I end with 2 sodiums bonded to 1 carbonate and 1 hydrogen bonded to 1 hydroxide. And now I got to fix everything. So I'm going to save my H for last, and I'm going to address aluminum. Whoa. I think I definitely did a brain fart here. Did I do a brain fart? It's aluminum too. Sorry. Did I write that funny over there too? No, I just wrote it funny here. Okay. How bizarre. Okay. It's aluminum 2. Carbonate 3. Okay. No one was gonna say anything. No, none of you were gonna say anything. Just let me do that. On the what?
The little one you put an N in instead of the.
What's the little one?
Like six. Yeah.
Oh. Thank you. Aluminum carbonate. There we go. Okay, now we're good. Wow, now we're good. So now I'm going to address just my aluminums. I'm going to multiply my reactant aluminum by 2. But if I multiply that by 2, I have to multiply my hydroxide by 2. Hi, Will. Okay, she's right behind you. Eliana? Okay, so, okay, so I balance my aluminums. Great, but I create a new problem with my hydroxide. Not so great. So I'm going to now balance my hydroxides. So to get to 6, I'm going to multiply this by 6, the product hydroxide, which means I also have to multiply my hydrogen by 6 on the product because it's attached to that hydroxide. It's in a bond with that hydroxide. So then I say, okay, now I'm at 6 and 6 hydroxide and 2 and 2 aluminum. But my carbonates and my hydrogen are not balanced. So I'm going to multiply my carbonate by 3. And if I multiply my carbonate by 3, I also have to multiply my hydrogen on the reactant side by 3. So I get 6 and 3. Oh, looksy dooksy. Isn't that nice? It actually ends up working out for me because then I balance my carbonates and my hydrogens. So then I take my multipliers or my multiplication and I make those my coefficients. And I forgot to do this up here to show you guys. Okay. And so it becomes then, final answer, 2, 3, 1, not going to write that, and 6. So what does this translate to then? How would I say this verbally? 2 aluminum hydroxide compounds combine or react with 3 bicarbonate compounds to produce 1 aluminum carbonate compound and 6 water molecules. Okay, so if you guys haven't figured out the rest of them, I'm going to give you guys about 10 more minutes to see if you can actually get it correct, having looked through these first 2. All right, I'm going to give you about 10 more. Station 3 had rubidium solid react with rubidium nitrate to produce rubidium oxide and diatomic pure nitrogen. Now, Lachlan's going to actually introduce us to his method, which is a little different. Okay, totally fine if you create a different method. Just be very careful that your different method isn't so much of a shortcut that it actually sets you up for issues. But let's see what you got for us, Lachlan. So go ahead and walk us through.
Okay.
And sorry, let me turn off the timer.
All right.
There you go.
The first thing I look at is like the random elements on the side, like nitrogen, that are kind of bundled over here. And I can see that there's 2 and there's 1 here. So this one has to be double of this one. I'll just keep that in mind.
Could you write that down maybe somewhere? Just like this has to be times 2 of 1 or something, right? Make sure it's
Okay.
visual.
Of that?
Sure.
Cool.
Just give them a visual.
And then there's the only oxygens are right here and right here. And this one's this one is 3. Horrible. This one is 3 and this one isn't. So this one has to be times 3 of that one. So if we set that up, hold on. I'm gonna put mine is like literally just guessing and checking. It's just so random.
Okay, let's just watch what the guess and check method produces.
Okay, cool. I'm horrible at explaining this. So put 1 here, put 2 here, because that works for the nitrogen. But if we look at the oxygen, that makes 6 oxygens, because 2 times 3 is 6. So over here would have to be 6 to match up with that. But now we have 12 rubidium. And we need 12 more over here. We have 2 here, 5. Wait, hold on. 6, 12.
I think you mean 10 plus 2 is 12.
Yeah,
So,
that's what I'm thinking.
okay.
I didn't think I'd be up here. Does that all work?
He was on his phone. I thought I'd give him something to do. Does it work?
I think so.
Okay. Anyone have any qualms about the answer? Maybe the method we'll talk about in a second, but the answer?
Yes. Correct.
Is it correct? Okay. So, thank you. Take a seat. So, you could totally do guess and check. That is totally fair. I wouldn't, unless it's a very simple problem. Like, very simple, yeah, you can do in your head. I don't know. When you start breaking up a polyatomic, it gets a lot more complicated, right? Because now you got 3 factors involved that you didn't have before. So that's one method. Would you like to see my method with this one, or would you like to call it good? Okay. So Lachlan's method, I'm sure you guys have done in your head, which is totally fine. I would just be very careful. Very, very careful, but it did get Lachlan the answer. So if that works better for you, that is your prerogative. All right. So rubidium, I have 1. And then I have rubidium in a bond, 1 of them, with nitrogen, 1 of them, and oxygen, 3 of them. And I do not keep the NO3 together this time because I noticed that it's not preserved on the product side. So I split everything up. So I got to treat it as a split in the beginning. Then I end with rubidium 2 and oxygen 1 bonded together and nitrogen. So I start going through and I say, okay, well, nitrogen, I'm going to multiply this times 2, times 2, times 2. And I get, okay, 2, 2, and 6. I took care of my nitrogen. Now I got to take care of my my rubidiums. So my rubidiums are not equal right now. So I'm going to multiply. Oh, they're by 3. Right now I have a total of 3. You know what? I actually might say my rubidium last because I'm noticing that I have a solo rubidium, which I can easily adjust to compensate for anything else. So I'm going to actually save that for last, and keep in mind that I have solo rubidium, and I have right now 3 total rubidiums on the reactant, 2 on the product. I'm going to look at my oxygens first though, and I'm going to multiply my oxygens by 6, which means I can multiply my oxygen on the product side and the rubidium it's attached to by 6. So I get 12 and 6. So now I say, okay, now I have a total of 12 on the product for rubidium, but I have total of 3 on the reactant. So I could mess with the rubidium in the compound, but if I mess with the rubidium in the compound, I mess with everything else. And right now, everything else is actually balanced. All the other atoms are balanced. So I'm just going to mess with the solo rubidium because it doesn't matter what I multiply it by. It doesn't affect anybody else. So I have 2 and 1 on the reactant and 12 on the product. So I'm just going to multiply my solo rubidium by 10 to get it to be 10 plus 2 for a total of 12. Now I'm balanced. So it becomes 10, okay, 2, 6, and 1. And that is because I took my multiples. Yes. Normally, but this ended up being a little bit easier with the rubidium being the solo. I mean, it would have worked out no matter what. It actually, I just realized that it would have been a shortcut for us in this case, but it would have still worked out. Generally speaking, oxygen last, but here it just happened to look a little bit better. All right. You ready, Liam? Yep. Liam's going to walk us through the next one, because Liam and Lachlan decided to do this all in their heads. So I thought, why not show off their skill? Oh. Nope. Go ahead, Liam. Very tall. Let's raise it up for you.
So for this one, first thing I kind of noticed was that NH4 here and there's NH4 here, but there's 3 of them.
Nah, yellow is not the way to go, man.
Okay, there's
Mhm.
green. So we know that this one is ultimately going to have to be closer to this one. Like it's going to have to be equal, obviously, but that's just where my brain went to first. Also, there's another polyatomic, this one right here. Yeah, and then here, this one, which as you showed us was, yeah. So main one was that there needs to be 3 ammonium, so 3, and then if you see here, if there's 3 of that, then the what's that, hydroxide? Hydroxide would be 3 as well. So that would do that. Oh yeah. So if there's 3 of them, then there's 3 hydrogens plus the other 3 hydrogens right here, and that'd be 6. And for 6 divided by 2 is 3, so we put that there. And then kind of double check everything else. There's 1 phosphate, and then nitrogen or the ammonium's already solved. So that's
Okay, thank you. So again, that is how a method that you could use. And again, I'm sure some of you guys are already doing that in your head. Would we like to see it written out? Or you actually feel pretty satisfied with that? Okay. Again, it's totally fine. You got the right answer. It's totally fine. If that's how you think, that's how you think. That's totally fine. I would, again, just be very careful. Thank you, Liam. So Liam's absolutely right in how he identified, first of all of the polyatomics. That was an excellent step. He noticed immediately all of the polyatomics that are being preserved. So he should have noticed, okay, OH, NH4, PO4, NH4, PO4. And if you do separate water into HOH, then you also see that the hydroxide. So this is a huge polyatomic one. Then they're all preserved, which is really nice because can you imagine splitting all of these atoms up? That would get annoying. So it's really, really nice shortcut. So I say I have one ammonium attached to one hydroxide in the beginning, and it's going to react with 3 hydrogens attached to one phosphate to produce 3 ammoniums attached to one phosphate and 1 hydrogen attached to one hydroxide. And so then what you do is you notice, okay, I'm just going to tackle one of them. So I'm going to tackle ammoniums. I'm going to multiply this by 3, which means I multiply the hydroxides by 3. And I see, okay, so my ammoniums are balanced. Now I'm going to balance out my hydroxide. So I'm going to balance out by multiplying my product hydroxide by 3. But if I multiply my product hydroxide by 3, then I multiply my product hydrogen by 3. So I get 3 and 3. Okay. And so then what I get here is, whoa, yep, perfect. Then what I get here is totally equal, totally even. Easy stuff, easy peasy, right? And I get then that everything is equal so that my coefficients become 3, 1. I'm not going to write that. 1, not going to write that, and 3. So what does this translate to verbally? 3 ammonium hydroxides react with 1 trihydrogen phosphate, whatever. There's like a technical, there's like a common name for it, but whatever, to produce ammonium, 1 ammonium phosphate and 3 water molecules, right? So, we'll save for tomorrow morning. We'll save these 2 reactions as warm up for tomorrow. And I want to get on to notes, so introducing types of reactions. So I'll make a little note to myself as a warm up. And this will be our warm up for tomorrow. And no, someone's up, so you have to wait. And let's switch over to notes. Types of reactions. That's our balancing. You guys have homework. You can do more. Some of you took photos. Maybe just do these at home so you come prepared tomorrow. Now you may go. And let's switch over to notes. Types of reactions. Good job, you guys. Okay. So now that we know how to write and balance reactions, theoretically, it's going to come with practice. Okay. And you do need to practice. One of the things about my class, Jenny, is that I do random homework checks that go to your score. And it's like kind of Russian roulette. Like if you decide not to do the homework that night, bummer. But you can always submit proof later that you did it. Okay. So now that we know how to balance reactions, it's kind of nice to group reactions into categories. Like I could write an endless amount of reactions for you, and you can balance an endless amount of reactions. But wouldn't it be nice to like actually know what type of reaction you're doing? Like now that you figured out how to do it, it's like, it'd be nice to be a little bit more selective about it. Like, hey, I kind of want this particular type of reaction. Like I want to build something. I want to do a synthesis reaction. So we're going to talk about the first 3 out of the 6. We're going to start with the fun one, and that's combustion. Combustion reactions is a category of reactions that occurs when a hydrocarbon, and a hydrocarbon is a molecule made up of carbon and hydrogens, okay? When a hydrocarbon reacts with pure oxygen to produce, okay, carbon dioxide gas and water vapor and lots of energy. Triangle heat, okay? This is a set reaction. This is a category of reaction that a lot of different reactions fit into, okay? So the example of kind of the general reaction would be here. We have methane or carbon tetrahydride reacting with oxygen to produce carbon dioxide gas and water and energy. Okay, that's what we have here. Good God. My arrows are real off. Okay. That's the generic example of a combustion reaction. The thing that changes when it talk about combustion is they're super easy to recognize. The only thing that changes is this hydrocarbon. The hydrocarbon tends to be the only thing that changes in combustion reactions, which means, of course, your coefficients are going to change based on how you balance. But as far as the actual molecules, all the rest of the molecules, you write that down. Done. Combustion, you always got pure oxygen, you always produce carbon dioxide, you always produce water, and you always produce a crap ton of heat. So hydrocarbons can include examples such as C2H6 or C6H12O6 or I don't know, more like C3H8, anything that has carbon and hydrogen. Okay, hydrocarbon. Okay. So one thing that we can note about combustion reactions is that we can also categorize them under an energy label known as an exothermic reaction. An exothermic reaction, notice this word ex for exit. An exothermic reaction is a reaction that releases heat, energy. So this would be a product. Heat would be a product. So combustion reactions are also always good examples of this other type of category of reactions called exothermic reactions. Okay. Please, 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 for your quiz on Monday, I am going to give you a series of reactants and you have to predict the products based off of the type of reactants, which means you have to be able to see what type of reaction it is. So if you see a hydrocarbon plus pure oxygen, immediately your brain should be combustion, which means your products are always carbon dioxide, gas, and water, gas, and heat. Like guaranteed, hands down. Based on the reactants I give you, you can predict exactly what's going to be produced. And then you balance after that. That's what your quiz on Monday is going to look like. And I'm going to quiz you on all 5 types of reactions. You have to be prepared. You have to know them well enough. Okay. So they always produce these 3 things. Like it is never changing. Like combustion, that never changes. Okay, second type of reaction is kind of what you think about with chemistry, synthesis. It's molecule making in terms of combining 2 things that are smaller and making something cool, more complicated. A synthesis reaction occurs when 2 or more smaller compounds are combined. So we also sometimes call it a combination reaction to produce a larger or more complex compound. So anytime we make a ionic compound from its raw elements, that's a synthesis. Okay. So general equation is A plus B goes to C. Okay. And where C is your more complex. Okay. So for example, here's some practice. Okay. AgN2, AgN2, pure silver reacting with pure nitrogen can form, if we're assuming silver is a charge of 1 plus, it takes on a charge of 1 plus. We're going to say this is Ag3N. Now, this is totally unbalanced. But that would be the synthesis that could be formed. NaCl2 can form 2 NaCls. That would actually be balanced. So I'm just going to write unbalanced for right now, NaCl. We'll come balance later. And pure sodium solid can react with pure phosphate gas to produce sodium phosphate ionic compound. These are all synthesis reactions. Notice something. Non-charged pure elements are making charged ionic compounds, charged ions, which, combine. So you don't always have to start with an ion. Sometimes the characteristic of your element changes to become like an ion so that it can create an ionic compound. But the original reactant ingredients, like if I bought it from a store, would be pure, neutral sodium, neutral phosphorus. And then when we put them in an environment together, they take on this new characteristic to react. They act ionically. They exchange electrons. They didn't start off as charge. They became that when they encountered one another. Kind of cool. So, third type of reaction is the exact opposite of synthesis. It's called decomposition. It occurs when a larger, more complex molecule, get where I'm going, molecule or compound, breaks down into two or more simpler molecules or compounds. So the decomposition of hydrogen peroxide into water and oxygen gas explains why if you have any hydrogen peroxide that's older than like 6 months and definitely by a year, you actually just have liquid water. It decomposes over time spontaneously by itself into liquid water and vaporous oxygen. So the moment you release a hydrogen peroxide bottle that's been closed for a couple of years, you'll hear a pfft. That's your oxygen gas leaving you with water. So that's why hydrogen peroxide definitely has an expiration date. If you want actual hydrogen peroxide, you have to definitely use it by then. And the moment you uncap that hydrogen peroxide, you've actually ignited and accelerated the decomposition process. So your expiration date in terms of viability comes even quicker the moment you open it. So theoretically, you could probably drink 2-year-old hydrogen peroxide, well, because it's just water. I think the taste would still be kind of gross, but yeah. So it's the opposite of synthesis. We could call it the reverse reaction. If we were to undo synthesis, if we were to switch the arrow direction, go non-conventionally, your synthesis products are your decomposition reactants. So you break down into simpler elements or compounds. Sometimes you break down into your pure element. So for products, what you want to check for is the diatomic molecules. You want to make sure that you know when you're working with a diatomic. Because if I say I'm breaking down into pure oxygen, I'm breaking down into O2, not just O. So the general equation is C breaks down into A plus B. Oh, how surprising. How bizarre. So opposite, NaCl breaks down into Na and Cl2 unbalanced. This is unbalanced. And P5 and O10 breaks down into P and O2 unbalanced. You will be given reactions where I only give you the reactants, and based on the information, you have to predict the products, which means you have to know what type of reaction it is based off of the reactants. Because knowing the reactants and the type tells you what the products are going to be, and then you'll be asked to balance it after that. That's what your quiz on Monday looks like. We will talk about the next 3 types of reaction categories tomorrow. And we're going to warm up with the last 2 balancing chemical equation practice as well tomorrow. And we're going to actually try to identify them. All right. So really good luck, you guys. Make sure you're still memorizing your polyatomics. Really good work, you guys. And good luck. That's what I meant to say.